TypeScript for Java and C# programmers. TypeScript is a popular choice for programmers accustomed to other languages with static typing, such as C# and Java. TypeScript's type system offers many of the same benefits, such as better code completion, earlier detection of errors, and clearer communication between parts of your program. While TypeScript provides many familiar features for these developers, it's worth stepping back to see how JavaScript, and therefore TypeScript, differ from traditional OOP languages. Understanding these differences will help you write better JavaScript code, and avoid common pitfalls that programmers who go straight from C# Java to TypeScript may fall into. Co-learning JavaScript. If you're familiar with JavaScript already, but are primarily a Java or C# programmer, this introductory page can help explain some of the common misconceptions and pitfalls you might be susceptible to. Some of the ways that TypeScript models types are quite different from Java or C#, and it's important to keep these in mind when learning TypeScript. If you're a Java or C# programmer that is new to JavaScript in general, we recommend learning a little bit of JavaScript without types first to understand JavaScript's runtime behaviors. Because TypeScript doesn't change how your code runs, you'll still have to learn how JavaScript works in order to write code that actually does something. It's important to remember that TypeScript uses the same runtime as JavaScript, so any resources about how to accomplish specific runtime behavior, converting a string to a number, displaying an alert, writing a file to disk, etc., will always apply equally well to TypeScript programs. Don't limit yourself to TypeScript-specific resources. Rethinking the class. C# and Java are what we might call mandatory OOP languages. In these languages, the class is the basic unit of code organization, and also the basic container of all data and behavior at runtime. Forcing all functionality and data to be held in classes can be a good domain model for some problems, but not every domain needs to be represented this way. Free functions and data in JavaScript, functions can live anywhere, and data can be passed around freely without being inside a predefined class or struct. This flexibility is extremely powerful. Free functions, those not associated with a class, working over data without an implied OOP hierarchy tends to be the preferred model for writing programs in JavaScript. Static classes. Additionally, certain constructs from C# and Java, such as singletons and static classes, are unnecessary in TypeScript. OOP in TypeScript. That said, you can still use classes if you like. Some problems are well suited to being solved by a traditional OOP hierarchy, and TypeScript's support for JavaScript classes will make these models even more powerful. TypeScript supports many common patterns such as implementing interfaces, inheritance, and static methods. We'll cover classes later in this guide. Rethinking types. TypeScript's understanding of a type is actually quite different from C# or Java's. Let's explore some differences. Nominal reified type systems. In C# or Java, any given value or object has one exact type, either null, a primitive, or a known class type. We can call methods like value.getType or value.getClass to query the exact type at runtime. The definition of this type will reside in a class somewhere with some name, and we can't use two classes with similar shapes in lieu of each other unless there's an explicit inheritance relationship or commonly implemented interface. These aspects describe a reified, nominal type system. The types we wrote in the code are present at runtime, and the types are related via their declarations, not their structures. Types as sets. In C# or Java, it's meaningful to think of a one-to-one correspondence between runtime types and their compile-time declarations. In TypeScript, it's better to think of a type as a set of values that share something in common. Because types are just sets, a particular value can belong to many sets at the same time. Once you start thinking of types as sets, certain operations become very natural. For example, in C#, it's awkward to pass around a value that is Either a string or int, because there isn't a single type that represents this sort of value. In TypeScript, this becomes very natural once you realize that every type is just a set. How do you describe a value that either belongs in the string set or the number set? It simply belongs to the union of those sets, string, number. TypeScript provides a number of mechanisms to work with types in a set theoretic way, and you'll find them more intuitive if you think of types as sets. Erased structural types. In TypeScript, objects are not of a single exact type. For example, if we construct an object that satisfies an interface, we can use that object where that interface is expected even though there was no declarative relationship between the two. Interface point like x, number, y, number, interface named name, string, function log point like console.log, x equals plus point.x plus, y equals plus point.y, function log name, x, named. Console.log, hello, plus x.name, const obj equals, x, 0, y, 0, name, origin comma, log point, obj, log name, obj. TypeScript's type system is structural, not nominal. We can use obj as a point like, because it has x and y properties that are both numbers. The relationships between types are determined by the properties they contain, not whether they were declared with some particular relationship. TypeScript's type system is also not reified. There's nothing at runtime that will tell us that obj is point-like. In fact, the point-like type is not present in any form at runtime. Going back to the idea of types as sets, we can think of obj as being a member of both the point-like set of values and the named set of values. Consequences of structural typing. OOP programmers are often surprised by two particular aspects of structural typing. Empty types. The first is that the empty type seems to defy expectation. Class empty, function fn, arg, empty, do something? No error, but this isn't an empty? Fn, k10. TypeScript determines if the call to fn here is valid by seeing if the provided argument is a valid empty. It does so by examining the structure of k10 and class empty. We can see that k10 has all of the properties that empty does because empty has no properties. Therefore, this is a valid call. This may seem surprising, but it's ultimately a very similar relationship to one enforced in nominal OOP languages. A subclass cannot remove a property of its base class, because doing so would destroy the natural subtype relationship between the derived class and its base. Structural type systems simply identify this relationship implicitly by describing subtypes in terms of having properties of compatible types. Identical types. Another frequent source of surprise comes with identical types. Class car, drive, hit the gas, class golfer, drive, hit the ball far, no error? Let W, car equals new golfer. Again, this isn't an error because the structures of these classes are the same. While this may seem like a potential source of confusion, in practice, identical classes that shouldn't be related are not common. We'll learn more about how classes relate to each other in the classes chapter. Reflection. OOP programmers are accustomed to being able to query the type of any value, even a generic one. See hashtag, static void log type. Console.writeLine, typeoff, t name, because TypeScript's type system is fully erased, information about e.g. the instantiation of a generic type parameter is not available at runtime. JavaScript does have some limited primitives like typeoff and instanceive, but remember that these operators are still working on the values as they exist in the type erased output code. For example, typeoff, new car, will be object, not car or car.